Hi everybody. I hope you guys have been enjoying your time off. I'm sorry to say that, as you already know, we're not going to be in class again today on Thursday, and so I'm video recording another lesson. Unfortunately, I just recorded this whole lesson, and I went to render the video, and the file got corrupted, so I'm doing it all over again. So um, hopefully I'll be more efficient this time through, and it'll go a little bit faster. Make sure that you guys have checked out the web page and have printed out a copy of this packet that I'm working through, because that way you can take notes along with me, and it'll make it easier for you to learn the material if you have some paper in front of you that you can write on. Now, the big idea for today is taking what we learned at the beginning of the school week, which was inverse functions, and combining it with what I taught in the web lesson from yesterday, exponential functions. So if we take the idea of exponential functions and inverse functions, put it together, it's going to lead us to a new vocab word, the logarithm. And we'll get to that in a little bit, but I'm just going to do a little bit of review for exponential functions. We're going to graph f of x equals a to the x power, where a is a positive number. First thing they said is label the y-intercept of f of x. Well, that means you're going to take the number 0 and you're going to input it into your function. So a to the power of 0 equals 1. So it doesn't even matter what your a is for f of x equals a to the x. No matter what it is, you're going to have a y-intercept of 1. What is f of 1? Well, f of 1 is a to the first power, which is just a. Now that's a little bit harder to graph because I don't know what my a value is. I just know that a is some positive number bigger than 1. So, just kind of making something up here, but maybe it's somewhere around there. Now, as x tends to infinity, where does f of x tend? So what this is saying is, for larger and larger inputs into our function, what happens to our outputs? So for example, I might do a to the first, then a to the 10th, then a to the 100th, a to the 1000th, etc. And for an a value that's bigger than 1, what's going to end up happening is we're going to tend to infinity. It kind of makes sense, right? Like, let's say you had the number 2, maybe your a value was 2, 2 to the first, 2 squared, 2 cubed, 2, maybe to the 1 million. As your powers are getting larger on your base of a, eventually that's going to tend to infinity. As x tends to negative infinity, where does f of x tend? We could try to figure that one out as well. This time a to the negative first, maybe a to the negative 10th, a to the negative 100th, even a to the negative 1 millionth. So as we have more and more negative powers on our a value, we're trying to figure out what happens. Well, let's say we had 2 to the negative 100th. That's the same thing as 1 over 2 to the 100th. You can see that you're going to have ever closer to 0 fractions. You're dividing the number 1 into more and more pieces. So you're tending to 0. So let me write that down. There it is. Okay, and we could even get a nice little graph of it. So we've got a horizontal asymptote at y equals 0. Then our function starts to grow very, very quickly and heads off to infinity. Now, what is the domain and range of f of x? That's something we talked about yesterday, but the domain of f of x equals a to the x is going to be all real numbers, from negative infinity to infinity. I can pick any value I want to for x and input it into the function f of x equals a to the x, and I'll get an output from that. So that's perfectly fine. But our range is actually only going to be from 0 to infinity, because we have a horizontal asymptote at y equals 0. There is no number that I can input into the function a to the x to get 0. nor is there any number I could plug into a to the x to get a negative number. So my range has to be from 0 to infinity. Problem 2 is very similar. I'm going to graph f of x equals a to the x, but now I'm going to say that a is some number between 0 and 1. It'll change things a little bit, but the same sort of techniques are going to be used. So first, label the y-intercept of f of x. Well, f of 0 is a to the 0th power, which equals 1. So we still have our same y-intercept at 0, 1. F of 1, same idea again. F of 1 is a to the first, which just equals a. But now, as x tends to infinity, where does f of x tend? Well, we're doing the same sort of idea, you know, a maybe to the 10th, a to the 100th, a to the 1000th, bigger and bigger powers on our a. But this time a is a number between 0 and 1. So it's not going to behave the same way as problem number 1 did. Say that your a was 1/2. An example would be a equals 1/2. Well, if you did 1/2 to the 10th power, then 1/2 to the 1000th power, 1/2 to the millionth, you know, let that power tend to infinity. Well, 1/2 multiplied by itself more and more times, that's going to be tending to 0. And then the reverse of that, as x tends to negative infinity, where does f of x tend? Well, a to the negative 10th, a to the negative 100th, a to the negative 1000th, etc., etc., a to ever more negative powers. Just remember, you know, I can give you a little example. Say that your a value was 1/2 and your power was negative 100. Well, that's 2 to the 100th power. You can see that that power is getting larger and larger and larger. As your exponent's growing, 1/2 to that power is going to get arbitrarily large. So as x tends now to negative infinity, f of x is going to tend to infinity. We have a similar sort of graph. It's just kind of reflected about the y-axis, which is something we talked about yesterday, because another way of thinking about this is if you have, say, 1/2 to the x, that's the same as 2 to the negative x, which would be the same thing as taking the graph of 2 to the x and reflecting it about the y-axis. Okay, domain and range, same thing. Our domain is negative infinity to infinity. Our range is from 0 to infinity. Okay, and here's a refresher on properties of exponents. The product property of exponents, if I have a to the x times a to the y, that turns into a to the x plus y. If I have a to the x all raised to the y, the power property says that you have a to the x times y. The quotient property, a to the x over a to the y, is a to the x minus y. And then the way that 0 exponents work is any non-zero number to the 0th power equals 1. Okay, so that's just a little bit of review with exponential functions. Let's take a look at problem number 3 now. Okay, we're going to graph f of x equals 2 to the x power, and we're going to answer a couple questions. So why don't I fill out a little function table. If I input 0 into 2 to the x, I get 1. If I input 1, I get 2 to the first, which is 2. If I input 2, I get 2 squared, which is 4. I can also do some negative numbers in my function table. 2 to the negative first is 1/2. 2 to the negative second power is 1/4. And why don't I go ahead and graph it? Won't take very long. So negative 2 1/4, negative 1 1/2, 0 1, 1 2, 2 4. Now this thing starts to grow very, very quickly. By the time I get to 3, I'm up to 8, and then after that I'm already off the graph. So I've got this nice exponential function, 2 to the x power. However, the problem doesn't want us to stop there. They say fill in the table about the function and its inverse. So you can see we're going to be talking about the inverse to this exponential function. So remember the way that inverse functions work. What we talked about earlier in the week is that inverse functions switch your input and your output. It switches your domain and your range. It switches your x's and your y's. So to get my function table, to get my xy table for the inverse function, literally just switch the x's and y's around. 1/2, -1, 1, 0, 2, 1, 4, 2. And now I can go ahead and take those ordered pairs, and I could get a nice graph of whatever this function is going to look like. So I'm at 1/4, -2. I'm at 1/2, -1. I'm at 1, 0, 2, 1, and 4, 2. One thing that you guys might remember from earlier in the week is when you graph inverse functions, a function and its inverse, you're going to notice that there's symmetry about the line y equals x. And that's not by accident. It comes from the fact that when you get an inverse function, what you're doing is you're switching the inputs and the outputs. You're swapping the x's and the y's. So y equals x is going to be that line that you're going to be symmetric about. All right, so what we've just done is we took an exponential function and we graphed its inverse. And remember, we were just talking about how we can find the domain and range of an inverse. All you need to do is take the domain and range of the original function and you kind of swap it around, and that's going to give you your inverse. So let's try it. Sorry. There we go. So we're going to take the domain for f of x equals 2 to the x. I'm going to take the domain for f of x equals 2 to the x. That's -infinity to infinity. We're going to take the range from f of x equals 2 to the x. That's 0 to infinity. And now to switch over to our inverse function, all you have to do is swap your domain and your range. So for the inverse function, f inverse of x, my domain is from 0 to infinity, and my range is going to be from -infinity to infinity. Okay, remember that's generally how you do it. If you're ever asked to find the domain and range of an inverse function, just take your domain and range from your original function and swap them around. You're switching the x's and the y's. And there it is. We've got that graph. Now, this is going to be our entire focus for today. The whole point of what we're learning today, and in fact for the next few days, is talking about the inverses to exponential functions. And as I said, it's introducing a new vocab term called the logarithm.